We are going to open now the terminal installation session. Terminal installation is something very dependent on each terminal boxes and cabinets manufacturer. So we are going to give you only some highlights here. You have to check the installation manuals of each manufacturer and attend their training courses and certification so that STC recognizes you as a certified technician for the products delivered and manufactured by each specific STC supplier. The first terminal element that we are going to see is the FDT, which is the most important one in fiber to the home networks, and not only fiber to the home. Since 2014, with the adoption of fundamental planning, we are using the FDT as a fiber hub for all types of services within the FDT coverage area. So FTTM sites, point-to-point connections, serving key accounts, or even active cabinets such as MSANs or IPDSLAMs, they can be served through FDTs connected back to the exchange on the feeders. That's the meaning of having a bypass ODF in the FDT cabinet. So when it comes to the FDT installation, needless to say that only approved manufacturers are to be used for actual field installations. We are going to see the major points to take into account. They are listed here purely on the mechanical side of the cabinet. The FDT must be placed on the concrete base by a proper lifting tool. So do not lift the cabinet by hand. The cabinets have to be lifted by the proper tools, and the hooks provided, as you can see on the picture, to be lifted by a crane. Because of the multiple vendor base that we have engineered, we are using the same base with different anchor bolt positions to install different manufacturers' cabinets. So ensure that the cabinet you are installing corresponds to the settings that you have at the base with the anchor bolts. Inspect the FDT before installing it. No damage, scratches, rust, loose parts must be seen prior to the installation. If any of those are seen, you have to return the FDT and make it fixed or swap it by a new one. Check that the cabinet keys are available. The doors can operate, close and open without any issues, including the door stopper. The STC logo must be available, and according to the technical specifications, check that the installation manual is provided together with the cabinet. And for additional information, both on the FDT performance and functions themselves, as well as the utilization in the network, refer to the STC guidelines displayed on your screens. Now we're going to cross some words about terminal boxes. Terminal boxes, understood as the customer side boxes, are the endpoints of the OSP network closest to the customer end. So from those boxes where we terminate the fiber network, field operations teams later on install cable drops inside the house to provide service to subscribers. There are three types of terminal boxes: optical splitter boxes, optical distribution boxes, and fiber terminal boxes. All of them are wall mount. The OSB provides service to high density MDUs with a number of tenancies from 21 to 128. The OSB can host internally 1x32 or 2x32 splitters according to the materials technical specifications FT202. In most cases, the OSBs that we order from manufacturers equip one splitter, so their maximum capacity is 32 ports. Therefore, in order to complete the connectivity to 128 tenants, we need to install 4 boxes. Depending on the location where we installed those 4 boxes, we apply a solution or another one. The optical distribution box is addressing connectivity to low density MDUs with number of dwelling units between 3 and 20. They are specified in the FT201 document. Last but not least, the terminal boxes are addressing single dwelling units with a maximum number of tenancies of 2, even though we have 4-port connectivity in the terminal box as spare capacity for unforeseen cases of a villa expansion. You have some pictures down here as the terminal box that we already saw on OSB 32 ports and ODB 24 ports from different manufacturers. As we have 4 or 5 different manufacturers approved supplying these type of materials, please make sure that you are certified to install these materials by the manufacturers themselves within our qualification program. On this table on the top right corner, we have the general guidelines on the TB, ODB, and OSB utilization. So depending on the number of dwelling units described here, we have the drop cable fiber count in the mid column and the type of terminal box used at the right column. So for example, an existing building with between 3 and 8 dwelling units makes use of a 12 fiber cable and an ODB 12. If the number of dwelling units is between 9 and 20, the cable that we use is a 24 fiber drop cable and the ODB is an ODB 24. Buildings with up to 32 dwelling units but higher than 20 make use of OSBs. But in this case, with 1 OSB is enough because we have up to 32 dwelling units serviced by the OSB box. Last but not least, vacant lots and dual homing. Dual homing is the redundancy path provided to a parcel. Do not need to equip cable and terminal boxes. On this slide, we're going to review the terminal box installation when it comes to the coupling with the U-guard. The important point here is the U-guard dimension and how you install it not to harm the ducts and cables. So in the previous specification, this depth was 30 centimeters. Now in the new specification, this is only having 10 centimeters. The reason being that we don't want the cable or the duct to be kinked at this position. If you pull this U-guard all the way down to 30 centimeters, it will be too close to the horizontal duct. So this radius is very sharp and we will be eventually kinking the duct and damaging the cable. Also pay attention to the fixing clamps distance, 200 millimeters from the ground, then 500 in between clamps and 300 millimeters between the last clamp and the terminal box installed. Make sure that you follow the installation manuals provided by manufacturers and get certified by them. Last slide on the terminal installation is to avoid the occurrence of this case in the field. Look at the cable exposed in between the U-guard and the box. This is a common mistake that we have to eliminate. All the efforts that we put to protect duct and cable by using an expensive U-guard are ruined if you leave this space between box and guard. Eventually, in this case, both photos are coming from the same installation. The exposure here comes from the lack of cover, but even though in many other cases with the cover installed, we see in the field that this gap is still existing. So pay special attention to that when installing the terminal boxes. We are going to move on to the earthing now. The principle with earthing is that metallic components have to be grounded. The copper network is a metallic network, so all metallic cables needed to be grounded. The same happens with fiber metallic armored cables. Nowadays, those metallic cables are not allowed anymore. So even for long distance and junction, the cables have to be ducted. However, there are a few cases where we need to take into account the earthing and bonding, unlike the copper wire where everything had to be grounded. One of these cases is shown here on the drawing. This is the repair of a former armor cable section. So if this section needs to be replaced, this new cable is dielectric, is not going to be containing any metallic components. So the metallic parts of both ends of the former cable have to be grounded at these locations. Apart from that, another point that we have to take into account for earthing is the metallic cabinets. Metallic cabinets in the copper world were also grounded, and even though in fiber we don't have metallic transmission components, we keep the grounding procedure not to get the crews confused when they are installing cabinets in the field. So both copper and fiber cabinets need to be grounded. In addition to that, we are going to detail some specifications about the minimum resistance of the grounding connectivity. What we are looking for is an earth resistance between 5 and 10 ohms. This is the acceptable value. How to achieve these? Well, there are different procedures that you can follow as described down here, depending on the type of soil, sand or rock, or more or less difficulties in getting the expected earth resistance. We have to apply different technical solutions. Connectivity and patching. The connectors are key components in the fiber networks. Often forgotten, are a key element that have to be treated with care and clean at every single installation. It is critically important, as I said, the proper installation of a connector, but it's also critically important the performance of the connector itself. You can see that in the ITUT L36. The ITUT L36 specifies the fiber connectivity elements. STC connectors are grade B1. The letter stands for the insertion loss that the connector is introducing into the optical budget, and the number behind stands for the reflectance. So grade B1 connectors are specified in the L36 recommendation. Grade B means that 97% of the samples tested are within 0.25 dBs insertion loss. The reflectance, the one in the grade B1, corresponds to at least 60 dB return loss. I will not insist enough on the fact that the connectors are the most critical piece of equipment in the outside plant. Please clean the connectors every single time. Here on the right hand side of your screen you have the main standards applicable to connector performance and connector cleaning. Please check out the connector cleaning standards so you make sure that you are following the right procedure while cleaning. Now we're going to talk about some best practices to manage patch cords during installations. First, a note on the cable ties and patch cord management. Cable ties are often misused, especially the plastic ones can be easily over-tightened if you guys tighten them with machinery. So if you are using plastic ties, do not tighten them with any machine or any pliers of any kind. Do it with your hands. That would eventually prevent from over-tightening them. Preferably, instead of using plastic zip ties, use Velcro-based ties. The Velcro-based ties are preventing the over-tightening. Best practices to manage patch cords in installations. The purpose is to make sure that the patch cords are properly installed and not at risk. Avoid too many patch cords bundled together. That would be eventually forcing the tie cords to be over tightened. If there are too many patch cords together, that would be probably causing some macro bends in the fibers. Avoid mounting cables in locations that block access to other equipment. For example, the front panels of the ODFs. Always follow the routing instructions given by the manufacturer. Do not stretch the patch cords by twisting them, pulling or stretching them beyond its specified pulling load, maximum tensile load. Also, the minimum bending radius of the patch cords has to be respected. Creating tension in suspended runs is also stressing the patch cord, so it should be avoided. And stapling or applying any pressure with cable ties is also creating patch cord stress. Avoid leaving patch cords on the floor. Avoid as well any patch cords exposure to direct sunlight and moist areas. Keep patch cords in their bags and capped. Do not remove the dust caps from any connectors unless you are using them. Use the horizontal and vertical cable guides of the equipment as well as the cable spools to avoid kinking and sharp bends. Always use the correct length of patch cords according to the manufacturer instructions. The following slides are talking about inside plant cabling. Most of these statements come from the copper world. Most of these rules were engineered and targeting copper cable plant, so they do not really apply for fiber.
For instance,
cable weights in fiber technology do not have anything to do with copper cable weights. So there are many rules that are just legacy rules. So we are going to fly over it. The point here on the inside plant cabling is that inside plant cables are low smoke, zero halogen or plenum rated cables. In order to transition from the outside plant to the inside plant cables, there is something in between, particularly in large buildings and exchanges, called cable vault. Cable vaults are large chambers where the outside plant cables are spliced to the inside plant cables running deep inside the buildings. In some cases, we allow as well to keep using the outside plant cables inside plant, provided that we install corrugated indoor rated tubes protecting the cables. On this slide, you can see some large cable vaults showing the orange pipes that we were talking about before. These pipes allow the outside plant cables to be routed inside plant without having to change the type of cable and without having to splice them in the vault. Identification and labeling. The main theoretical concept that you have to keep in mind is that all network assets are identified at design stage. So the NE designers generate the codes for those network elements. So during implementation phase, those labels cannot be changed by the implementation staff. If any changes are required, the project has to be reviewed by the designers so that those changes are properly included, because the labeling comes from specific systems handled by designers. On the labeling requirements, STC has specified some rules listed down here. All labels have to be durable and resist fading. Shall be marked with permanent ink for the non-metallic types or embossed on metallic tags. The metal tags labels have to be aluminum or stainless steel. The non-metallic ones have to be specifically approved by STC. Size, color and contrast would be visible during normal maintenance activities. and they have to be directly readable without twisting them. The fixing elements must be resistant to the environmental conditions: moisture, heat, ultraviolet light, sun radiation. So they have to be fixed in a way that prevents any fiber damages inside the elements. The cabinets and covers must have the labels visible behind the covers. The labeling must be machine printed or embossed if the labels are metallic. Use upper cases and occupy the entire label area. The preferred font is Arial. Last point, do not expose repeatedly the labels in physical contact with other elements. Keep in mind that handwriting for labels is not allowed. They have to be machine generated. There is only one exception that we will see later on. Some important rules instructing how to correctly install the labels at the proper locations are shown on this slide. So we have an example of a handhole with a splice closure and a cable slack loop. This is the bird view, vertical view. This down here is the exploded view. So we have the A, B, C, D size in the manhole represented here, E, B, C, D sides. So you can see that we have two cables, a blue one and a green one. And you also notice the locations where the labels are placed. Every single time that a cable gets in or out the handhole, it has to be labeled. You see that the blue cable is spliced to the green cable in the splice closure. So the blue cable gets in the handhole, is labeled, goes to the splice closure, and the green cable gets out and is labeled as well. Both cables are labeled at the splice closure, at the handhole entrance, as well as at the cable slack loop. Mandatory rules to follow. At the manhole entrances, the cables have to be labeled between 20 and 60 centimeters from the duct inlet. So this distance here is between 20 and 60 centimeters. When it comes to the splice closures, the distance, so this distance here between the closure inlet and the label itself, has to be within 40 centimeters. If you have to keep in mind for practical purposes just one figure, you can think of the 40 centimeters as the standard, meeting the requirement for the duct entrance and cable labeling in between 20 and 60. And also meeting the 40 centimeters of cable labeling. Additional to those rules, a tag or a label must be placed on cables at the basements of the FDT, where the cables are exposed and coming up from underground.
Also,
at the entrance of racks and cabinets, such as ODFs in the exchanges or OSFs as well, where a cable is presenting diversity, so two different connecting routes, the label, color, or other form of identification have to show the protective connection. The last point we have to make on this slide is that cable slack loops need cable identifiers as well. So you can see that these two cables in the slack loop have labels, obviously separated from each other, because each label is tagging a different cable. This is a general knowledge slide. STC coding is based on the Common Language Location Identification International Coding, called CLLI code. Just as an example, this CLLI code is structured, as you can see on the screen, with characters. The first four are alphabetic and represent the neighborhood or hey. For example, MRST would represent Montserrat. The second two represent the district. For example, RD represents Riyadh. And the last two are the serial representation of the building. They are numeric or alphabetic or a combination of both. 02 would mean building 2 in Montserrat Hay, Riyadh district. So the CLI codes are given to the network assets. Then when a cable has to be identified, it takes the origin and destination network element CLI code. So you have an example here. Then is the fiber number, CLI code of point A origin, CLI code of point B destination, number of fibers, the type of project, in this case a junction project, and the ODF identification. The ODF is identified according to these rules: floor, row bay, panel, and unit ID. The ports are also identified, and in the cable the strand numbers that are going to be connected to the ODF. Marker plates and patch cords have also to be identified. So here on your screen you see some examples of marker plates labeling depending on the network element that they have to identify. For long distance and junction networks, the marker plates are installed on marker posts. Obviously there is no network element visible above the ground, so these marker plates, that are metallic ones as you know, are installed on marker posts. They show the information that you have on your screen: district exchange ID, site ID and link name, the marker post number, the station number, manhole or handhole close to it, cable type and size, and host name. FTTH terminals, all type of terminals, FTBs, ODBs, OSBs, also follow a similar structure but based on the FDT CLI code. These elements are referenced to the FDT they are connected to. Site ID and CLI code of the TB or OSB itself, and then the FDT number, ODF number inside the FDT where these elements are connected to, also the port number of the FDT, ODF, the splitter number and the splitter port. All these are then FDT references. Last but not least, you have the terminal or FTB number. Key accounts and FTTM sites follow a pretty similar labeling, but without the FDT information displayed on it. So the plate is actually showing the exchange where these elements are connected to instead of the FDT. A note on where to install the patch cords tags: to be installed within 20 centimeters from the connector or coupler they are connected to. The closest possible to the ODF, to the connectors, but without causing trouble to other patch cords. Just keep in mind that they should not prevent from mating other connectors on the ODF. For cabinets and rack labeling, each cabinet and rack has to be labeled at the top, front and rear, at the bottom, front and rear, with its own identifier. The labels have to be large enough to be easily readable and machine printed. The label characters have to be in contrast with the background. The identification and labeling of splice trays and organizers is the only exception to the handwriting labeling according to the splices and connections that you have made. The handwritten labeling is allowed, but always using capital letters and a permanent marker. ODFs have to be marked as well. Typically ODFs and OSFs are already labeled by the manufacturers according to STC numbering guidelines, although the patch cords connected to them must be labeled by you. In some cases it may be required so that the contractors label the ODFs. Splitters have a special labeling to be placed on top of the splitter body, indicating the splitting identifier. Then the splitter legs, so the pigtails that are coming out of the splitter cassette, have to be labeled by the manufacturers as well, according to the input and output port number. You have to connect the splitter legs to the right ODF positions according to the fiber junction schematics provided by the designers. Here you have some examples of labels and labeling machines. from the typical ring marking mechanism, very flexible and used for many years already, or laser printed on metallic tags, stainless steel laser engraved on the left hand side that are the preferable ones, the aluminum embossed labels, and some machines, handheld portable printers to print plastic labels, self-laminating labels, heat shrinkable labels. There are many types, but the preferable ones, as we said, are the laser engraved stainless steel tags.
Optical testing.
We are going to see first some instruments that we require for optical testing in STC. On this slide we have optional test equipment. This is not mandatory. No handover or pad test requires to use these instruments, but they are very nice to have for troubleshooting and fiber identification. They are really very useful. The first instrument is the Visual Light Source, VLS, also called Visual Fault
Locator.
These instruments are basically a laser light source in the visible spectrum, red light, 635 nanometers. They come with a set of adapters so that they can be plugged in any type of connector. Then inject the visible laser signal to reach in the range of 5 to 7 kilometers. Then they are very effective to identify what fibers are connected where. For example, when plugging the VLS onto a TV, you can immediately know what FDT ODF connector is connected to the TV because you see the red light coming out. In addition, if any microbends or fiber breakages have happened, especially in patch cord and back panels, you can easily see that because the light gets out of the breakage so that you can easily identify where the microbends and breakages are. The fiber identifier shown on the slide is another instrument providing similar functions as the visual light source. The way it operates is slightly different, but the functionality is pretty much the same. These instruments have some additional features like detecting 270 Hz, 1 kHz and 2 kHz modulated tones. They can indicate the presence of traffic as well on the fiber and the direction of the transmission. The way they work is that they pinch the fiber, as you can see on the photo, so they introduce a slight attenuation in the 0.15 dBs. On this slide, we are now going to talk about the mandatory test instruments. These are the ones really required to perform the STC handover testing. Two types of instruments are required. This is an OTDR field version. The OTDR is an optical time domain reflectometer used to characterize and troubleshoot fiber networks. The OTDR works by injecting a pulse of light at a predetermined wavelength and width, so pulse duration, and measuring the backscatter light. So the information provided by the OTDR is calculated. It's not really a measurement like you could understand a meter tape is measuring length. It's not that way of measuring. The OTDR interprets the backscattered light coming from the fiber and estimates, calculates what is happening in the fiber. The OTDR provides readings on the type of events, insertion loss, and distance events such as connectors, splices, or any type of bends are detected by the OTDR and shown on the screen with an estimated value of their amplitude and distance from the OTDR. The OLTS, the optical loss test set that you have down here, is actually measuring optical power level. These equipment typically are two different devices. One of them is a laser source The other one is an optical meter. On this picture, you have both functions integrated in the same device, but these are high-end devices. The high-end devices come with more features, but they are not really required for STC testing purposes. An important point is that these two devices have to operate at the same wavelength. So whatever the wavelength you set on the transmitter, you have to set it in the receiver. Unlike what happens with the OTDRs, the OLTS is actually measuring. So the OLTS measurement is more accurate than the measurement estimated, calculated by the OTDR. But the OLTS does not measure distance. It only measures optical power. We're going to see now more specifically how to use the OLTS. The light source is a simple laser light source set to a specific wavelength. The power meter is measuring optical power in the incoming signals. So an important parameter when selecting the power meter is the sensitivity. The sensitivity is the minimum power level that the instrument is able to measure. Make sure that the power meter sensitivity is good enough for the type of network that you are characterizing. The long distance networks and FTTH networks, because of the splitters, present a high attenuation. So not all power meters may be capable of providing measurements for those type of networks. Sensitivity is the first parameter you have to pay attention to. The dynamic range is the second one. Dynamic range is the difference between the maximum and minimum measurable input power. Obviously, if you inject too much power to the instrument, you will overload the receptor and eventually damage it permanently, depending on the level of the signal. Those two are the most important parameters. It is always preferable that these devices have some additional features. For example, intercommunication capability, so that you can communicate with each other without using phones or any other devices. Also, the VFL functions is also nice to have, but the mandatory requirement is that they operate at all wavelengths determined by the GPON protocol, 1310, 1490, and 1550. 1550 is the testing lambda. We are not transmitting traffic at this wavelength. Traffic is transmitted at 1310 and 1490, but all three wavelengths are required. So now we are going to see how to operate the OLTS, and there are two ways of doing this. The power meter can measure absolute power and relative power. Absolute power is measured in dBms, dBs per milliwatt in telecom transmission. Relative power is measured in dBs, decibels. The absolute power does not require the utilization of a light source, because the power meter is simply measuring whatever the power level is in the reception port
at a given wavelength.
However, when you measure relative power between 2 points, which is typically the case in telecom networks, we are measuring the attenuation introduced by an optical link between 2 points, A and B. This is the fiber under test. So relative power is the comparison of power levels between 2 points, in this case point A and B. Therefore, in order for this power meter to give you a direct reading on the attenuation between A and B, you have to set the zero reference at point A. It doesn't matter what the absolute power level at point A is. What matters is that point A is set to the zero reference for the power meter. This process is called zeroing, and that can be done in different ways. If you are certified by the Fiber Optic Association, Big C, or any other certification bodies, you will know the methods to do that. For the purpose of this training, we are not covering all those possibilities. We're just gonna say how to do this in a simple way. Set the light source to a reasonable power level, depending on the expected attenuation and the sensitivity of the power meter. Connect this optical power meter through the reference patch cords with very high reliability and performance. They are not any type of patch cord. You connect them together at point A. Set your zero reference, pushing on the button, and then this power level at point A will automatically become zero for the power meter. One more time, regardless the actual absolute power present at point A. Once the zero level is set on the power meter, reconnect the connector at the original position, and the figure that is shown on this power meter screen is directly the attenuation between A and B, including the connector B attenuation. In this case, the attenuation introduced by connector A is not taken into account.
So it will have to be added.
This is the way this device operates to measure relative power. Once you know how to operate the OLTS, we're going to see now in details STC requirements when it comes to testing the optical networks. The requirements are very similar across projects, but there are some differences. So on this slide, you have the long distance junction and point-to-point projects. There are 4 tests: cable acceptance of delivery, cable pre-installation, cable installation, and commissioning, which is the same as PAD. The cable acceptance on delivery is a mandatory test. The commissioning test is also mandatory. The other 2 tests, cable pre-installation and cable installation, are optional, but recommended if you guys have seen that during transportation between the warehouse and the site, something happened and eventually the cable drum got damaged, then you're suspecting that the fibers may be affected. The same while installing the cable. Maybe the cable got stuck in the duct and you had to push and pull back and forth. The outer sheath was damaged or the cable kinked and you are suspecting that something went wrong, then this cable installation test is a must. In other cases where the transportation and the cable installation goes smoothly, it is optional. The cable acceptance on delivery. This happens when you get the cable drums delivered to your warehouse. Then you have to test 1 fiber in each tube of the cable with the OTDR in a unidirectional way at 1550 nanometers. What you're expecting there in terms of events is just the pure fiber attenuation slope. The intrinsic fiber spectral attenuation, the expected figure at 1550 has to be lower than 0.22 dBs per kilometer. Then the cable pre-installation, which is not mandatory, as I said, is done exactly the same as the previous one, and the result expected is also exactly the same. Fiber attenuation slope lower than 0.22 dBs per kilometer. On the cable installation test, we have to measure all fibers, not only 1 fiber per tube. This test is still unidirectional, but is performed on all fibers and at 1310 and 1550. Then we have a little bit of extra margin because the installation may have affected the fiber performance with macro bends. So the fiber attenuation slope at 1310 is 0.37 dBs per kilometer and at 1550 0.25 instead of 0.22. Last test and most important one is the commissioning or PAD test. You have 2 types of tests here, the OTDR first and the OLTS second. These tests are done on a terminated network with all splices and all connectors already installed. So the test is mandatory, required on all fibers bidirectional. So from A to B and B to A at 1310 and 1550, And here you are expecting events because there are splices, connectors, potentially macrobands. So the fiber attenuation slope is a little bit more tolerant. It has to be within 0.4 dBs per kilometer at 1310 and 0.3 dBs per kilometer at 1550. No attenuation event has to be seen on the OTDR trace bigger than 0.2 dBs at 1550. So that is reducing the impact of the macrobands. Then on the splices, the maximum value allowed is 0.1 dBs as an average. There may be splices with higher attenuation than this, but compensated by other splices with lower attenuation. The absolute maximum attenuation allowed for a splice is 0.15 dBs. Then we are also expecting the connectors events in the OTDR trace. And remember that we are talking about grade B1 connectors. The maximum insertion loss value is 0.25 dBs. And also remember the reflectance, okay, is 60 dBs. For the optical loss test sets, the test is done unidirectionally at 1310 and 1550, and the end-to-end attenuation has to be according to the expected engineered value. We cannot define a specific value here because it depends on the link length. There is an engineered value that was provided by design, and then the end-to-end attenuation has to be within that value. For the FTTH type of projects, so point to multi-point, the required measurements slightly change. We have, first of all, a preventative testing that is exactly the same as the one that you have seen previously for point-to-point cable acceptance on delivery and cable pre-installation, with the exception that we are measuring a different fiber attenuation slope, 0.25 dBs. Then the cable pre-installation, again, is not mandatory. Remember, is only performed when you suspect that during transportation from your warehouse to the site, something happened with the cable drum or the cable itself. For the feeder specifically, the feeder section test could be considered as well as a point-to-point connection between the ODF in the exchange to the FDT, and it's not mandatory, and is the same type of cable installation test as long distance junction and point-to-point. On the feeder termination, there is a mandatory tests to be performed, and the feeder cable termination includes the FDT splitters. So it has to be done between the OSP ODF in the exchange and the distribution ODFs in the FDT. So this test is performed with the OTDR on all fibers. It's a bidirectional test. At 1310 and 1550, the fiber attenuation slope expected is at 1310 0.4, at 1550 0.3. No microband is expected on more than 0.5 dBs between 1310 and 1550 when you compare both traces. And then the splice insertion loss, as we explained before, is 0.1 dBs. The connectors are grade B, so their performance has to be exactly the same as before. 0.25 dBs, insertion loss at least 60 dBs overall. And then when it comes to the expected insertion loss of the FDT splitter, the maximum accepted value is 18.2 dBs. On the distribution and drop side of the FTTH network, between the distribution ODF in the FDT and the ports in OSBs, ODBs, or TVs, we have two types of measurements. The distribution and drop cable termination, performed after installing and terminating all cables on connectors, is a bidirectional OTDR test on all fibers performed at 1310 and 1550. The fiber slope has to be between 0.4 and 0.3 for 1310 and 1550. No variance higher than half dB between the traces at 1310 and 1550 at any event to prevent macrobands. The splices 0.15 dBs, connectors grade B1, exactly the same. The last test is the access commissioning, the PAD test. This is an OLTS test performed on all fibers by bidirectional testing, although it's unidirectional, could be in some cases accepted, performed from the ODF at the central office to the terminal box connector in the customer premises. It's an end-to-end test. So the overall insertion loss that we're expecting is 26.5 dBs, including the inside plant attenuation. But because the test is performed between the OSP-ODF and the terminal box, that optical budget is reduced to 21.5 dBs for the OSP part. We will see that in details on the next slide. As you can see on this slide, the OSP implementation budget is 21.5 dBs. The 26.5 budget stated in the guidelines is from this point to this point. The GPON Class B standard end-to-end optical budget is 28 dBs. So from the OLT port to the ONT port, the two active equipment, the two electronic equipment, we have 28 dBs as optical budget. Out of these 28, we leave 1.5 dBs for field operations budget inside customer premises wiring. If we remove the 1.5 dBs from the total budget, the remaining is the 26.5 dBs stated in the guidelines. Now, because we are only dealing with OSP testing from the OSP-ODF to the TVs, we have to remove the 5 dBs that the inside plant optical components, connectors, splitters, patch cords, consume. All these counts for 5 dBs. And then what we leave for the outside plant is the 21.5 dBs that I have mentioned earlier, from the OSP-ODF in the exchange to the terminal boxes on the customer premises. Because we are also allowing to do the optical absolute power test measured at the TVs, the reference at the TV level is minus 25 dBms absolute power, and knowing that the OLT transmitted power is in the range of plus 1.5 dBms. If we add plus 1.5 dBms to minus 26.5 dBs of attenuation at the TV box, the minimum optical power that we can measure is minus 25 dBms. Thus, in other words, an optical budget of 21.5 dBs measured between these 2 points corresponds to an absolute power of minus 25 dBms at this point.